Good evening everyone, I am Mr. Ish. Thank you for joining me for this video on sphere volumes. We're looking here at the derivation of the sphere volume formula right here, 4 over 3 pi r cube, and you can use integral calculus to very well do so. We've up till now looked only in terms of integral calculus at areas, the concept of areas, but the concept of volume is not too much different than that of areas. You're just adding this extra dimension of breadth, or you can call the word depth, the extra dimension of depth, to create that three-dimensional aspect which is represented very well by volumes. And the way you can do so is by doing rotation of curves or some sort of movement or dynamic movement of curves. We will do all of that here with this volume for a sphere, and we will look at this concept again when we actually get into the topic of volumes of curves. When we actually get into that topic, we'll talk about it in a more formalized manner. Here we're just looking at it in an introductory manner. If you have a unit circle and you know it's very well represented by this x squared plus y squared is equal to r squared. When you solve hypothetically as you would be for an area, you would solve here either in terms of y or an x, but let's look at everything here in terms of y. Y is equal to r squared minus x squared. This radius could be anything, and then you know you're ending up looking at the area of that, and you always have to multiply by 2 to capture the whole area, but we're looking here at an interval from minus r to plus r. The difference between here area and a volume is you don't have to do these extra steps you do for an area, but you have to look at things from a different perspective. Just take the same equation and graph it out. Y is equal to square root of r squared minus x squared. And it doesn't matter what your reference axis is, but for the sake of this video, let's look at this x-axis and we do a rotation about x-axis. See capital R for some sort of rotation or dynamic movement about x-axis of your curve of interest. If this is my curve of interest, y equals square root of r squared minus x squared, and I rotate this curve about the x-axis, what does the resultant figure look like? You can imagine you're drawing it and then you're rotating it such that you're getting these type of movements develop. You connect them over here and you end up getting what looks like a sphere. You've taken a two-dimensional aspect, or you can say just you've taken a curve and you've rotated it like this around a pivot, your pivot here being your x-axis, and you very well develop a sphere. We have to use integral calculus to determine the volume of this, knowing that the formula for a unit circle is x squared plus y squared equals r squared, but we've converted that into this form, and we can do everything here with regards to dx with what you know, y equals format equations, and you'll have an interval along the x-axis from minus x to positive x, which in this case will be minus r to plus r. And how can we go about deriving this volume? We can do so by understanding this single concept for volumes. Volume of anything that you're trying to determine is always equal to, from whatever interval a to b, the integration of areas along that interval of whatever shape that resultant volume is comprised of. If I'm looking at a volume of sphere, I can draw these two-dimensional areas, and there could be an infinite number or a finite number from this minus r to r, and if I were to take the cumulative areas from right here all the way up to here of all of these circles that form, you can imagine there could be a countless number of circles, and I were to add all of those areas from again this interval to this interval, I'll get a resulting volume determination, and that's how we're going to do this question. If I take this figure right here and I blow it up, let's just blow it up, and we just look at just a single circle which we can just draw. There are many ways of doing this, I'm just showing you but one way. And I pluck this little circle out and I pluck it out. I'm looking at something like this. It indeed is a proper circle, it's just you're looking at an angle. This circle of course will happen to have a radius. It will have a radius over here, and to determine the area of this one circle, you know it's pi r squared, whatever that radius might be. You do the cumulative sum of all of these areas from this minus r to r, you add them up, you'll get your volume. Let's modify this graph yet again, and let's talk about everything now in terms of what we will feed into this integral right here. We have what is looking like this. Y equals square root of r squared minus x squared. This represents the distance from any point along this x-axis from this interval to this interval upward right here will always be represented by this, because this represents the curve of this r squared minus x squared root is represented by this curve with relation to this x-axis. So at any point from this line from within this interval up towards this curve is always having a distance of this r square minus x square root. But this distance we're talking about is very well equivalent to what we are looking at now, the radius, which tells you what? That this radius over here, let's just actually not use r, let's use the symbol here y. Y over here is equal to my radius, and this radius is equal to a certain length from any point on this x-axis up to this curve, and it's equal to r square minus x square. Think about it. You can draw a little circle over here, and we're looking at the radius of this circle. We can call that y, and this circle which we have should have an area of pi r square, except here I'm using y as my r, so we should have a pi y square, because y here is represented by radius. We already know now what the radius is. If you plug this into place of y, which is represented by your radius, you have r square minus x square root and square. The square and this radical counteract one another. You just get pi r square minus x square, and now we suddenly determine the function which will feed into this integral, and we will feed it in and we'll take this calculation through. What happens? We're looking here now at a volume determination. You can even be more specific and say volume with regards to x, because all of this can be done with regards to y and then dy, but we're doing here with x dx. What is our interval? Our interval is from minus r to r. Minus r to r. We have this right here function pi r square minus x square, and it is a function by every means of the word, because a vertical line drawn through this specific curve will only cross it at one point. Pi here serves as a coefficient which can be pushed outside. Using the properties of integrals, you can convert this into this 2 0 r. You can modify this from minus r to r, from 0 to r, and bring a 2. Why? Because this right here is an even function. There's an equal dimension from here as it is from here. Minus r to 0 and 0 to r are equivalent. So you can just look from 0 to r and double it. And hence you have this. So now all of a sudden our integral becomes r square minus x square dx. And you know here the variable dependent and independent here are in terms of x. So when you're integrating this simple polynomial, we're bringing in x's. You have 2 pi r square x minus x cube over 3. We're using the n plus 1 over n plus 1. Simple integral polynomial template. So the r square yielded the r square x, because r square x to the power of 0, you bring in an x, a hidden antiderivative. Here you have x squared becomes x cubed over 3, again from an r to a 0. We have a 2 pi sitting outside. All you have to do is plug in these r's in places of x. You have an r cube minus r cube over 3. Do this simple fraction algebra right here. Common denominator 1, you have 3r cubed minus r cubed is a 2r cubed. You have a 2r cubed over 3. You open this up. 2 times 2 is a 4, times r cubed times pi is a 4 pi r cubed over 3. And this right here represents the volume of a sphere, which is what you wanted all along. So the only stretch of imagination here is, instead of looking at areas which are the areas below curves or between curves, you're adding an extra dimension to it. And that extra dimension graphically arises by some sort of rotational or revolutionary or dynamic movement of your curve about an axis or even a line of axis. It doesn't always have to be an x-axis or y-axis. It could be a horizontal line or any vertical line. But anyhow, you have a reference line around which your curve revolves. When you revolve it, you get the three-dimensional image. And within that three-dimensional graph, you can then start making these slices. Each of these slices has a representative area. Each of those areas is cumulatively added from the lower limit to the upper limit by this formula. And when you integrate this formula, you end up getting the volume determination for whatever figure that happened to form. And that's sphere volume here in a nutshell. 4 pi r cubed over 3, simple integral polynomial derivation. The most difficult part here is perhaps visualizing how the radius in this instance could be determined. And if you just understand that the area between the curve or area below the curve from your reference line of axis here being the x-axis represents the distance from that line of axis to the curve, and you just determine that distance is then equal to your radius, and the radius is what feeds through your entire procedure. The radius then goes to this formula pi r square or pi y square to give you the area of a single circle. That area of a single circle is cumulatively added through this integration or definite integration procedure to give you your volume, and that's that. Thank you for watching. Have a nice day.